Hi, everyone. Thanks for coming. So today's Colloquium speaker is Marc-Antoine Longpré.
Hi.
And so I've known Marc-Antoine for a number of years. I think he's maybe one of the world's experts on volcanism in the Canary Islands. And so there was probably many of you saw this eruption on La Palma a few years ago. So I think in some ways, I remember showing all the students in my class, like, this is happening right now. This is like a real world example of volcanic hazards. And it's not actually, I don't know, maybe I haven't measured, but one of the closer active volcanoes to us in a way. So Marc-Antoine got his undergrad degree at McGill and working with John Sticks, and I think still collaborates a lot with John Sticks. Got his PhD at Trinity College Dublin, and has been at Queen's College for about 10 years now. And he got a career award to investigate volcanism in the Canary Islands, and really also to get undergrads involved in collecting this data in a pretty unique way. So thank you very much. We're looking forward to hearing from Marc-Antoine.
Thank you so much, Ben, and thanks for the opportunity to share our work today. So it's going to be multidisciplinary. My expertise is in petrology mostly, but I'm going to try to tie this petrology work that we've done during the 2021 eruption together with geophysics, and then this leads us to talk also about fluid dynamics inside the volcano. So if there, at any point in the presentation, if you feel like you need further explanation, please let me know, and I can dig in a little bit more. I thought I'd start with this stunning satellite image of the eruption today that we're going to be discussing, and we can see here very clearly that this eruption was complex. Okay, there is this very low viscosity lava that we can see going down the slope, but at the same time there's this quite nasty looking plume testifying to this explosive activity that's going on. Okay, so it's a hybrid style eruption. I would like to begin by thanking my co-authors that have made this work possible. Special mention to Samantha Tramontano, who graduated last year from my group with a PhD, and she collected most of the data I'm going to be presenting today. Matt Pankhurst at InVolcan was instrumental in the field. InVolcan was monitoring the eruption closely in the field, and they organized this amazing sampling campaign that made our work possible. And Diana Roman at Carnegie, as well as Luca Doria, also at InVolcan, are helping me with the seismological aspects of the story that I've come up. Okay, so the plan, I want to talk a little bit about what is petrological monitoring, okay, why is it useful, and what are some of the challenges that we face when we want to monitor volcano from looking at the rocks, okay? But what also the opportunities that come up and what we can do in the future, okay? And that leads us to some of the research questions we're tackling using petrological monitoring. Then I'll give you a little bit of background on the case study, tectonic setting and things like that about the volcano. And then our approach, the different methods we used. And then the results are in three parts. The textures that we see in the rocks, then a time series composition of glass composition that we collected, and then also a comparison of this time series with geophysical monitoring data. Then I'll jump over to implications, and that this is where we have to talk about fluid dynamics, and then some conclusions. Okay, so what is petrological monitoring? Okay, so it's basically time series analysis of solid volcanic rock products that can complement traditional monitoring methods of volcanic eruptions, which are looking at seismicity, ground deformation, and gas emissions. Why is it useful? Well, petrology is unique in that it tells us about the properties of the erupting magma. Okay, it can only be done though in hindsight, and so traditionally, the challenge for it to be useful is a time challenge. Okay, so it takes a long time to analyze the rocks and put out the information. Okay. Also, a big challenge has been that the sampling, okay, of the rocks is done typically at low temporal resolution. Okay, so maybe we collect a sample that week of the eruption, and then we can sample next maybe 2 weeks later. So that makes it very difficult to compare with other monitoring methods that are near real time. Okay, so that's a challenge. But there's been new developments, okay, in both technological aspects, but also just the procedure of petrological monitoring that have made new advances possible, such that near real-time petrological data now are becoming possible and can directly inform eruption forecasting, hazard assessment, and decision-making during actual eruptive episodes. There's a couple of examples here from recent basaltic eruptions that made the news. So in 2018, there was this large fissure eruption at Kilauea volcano in Hawaii, and the Hawaiian Volcano Observatory there had a team of petrologists who went in the field and sampled the rocks, okay, every day pretty much, or as often as they could. And then they had an XRF, portable XRF instrument that allowed them to quickly analyze the chemical composition of the rock. Okay, and so in that plot over here, we see the calcium content of the lava over time, and that was done very, very rapidly and could be communicated to the authorities in near real time, and they were able to identify that a new influx of primitive magma was coming into the system, and that was useful piece of information. In Iceland, in 2021, there was also this interesting eruption, and which is off and off, continuing up until today. And these Halderson et al. In 2022 published this time series analysis that showed, from a trace element point of view, that the magma feeding this eruption was changing, okay, over the course of a few months of activity. And so that was also done very rapidly. There's a huge amount of possibilities when it comes to approaches to petrological monitoring, and this is a flowchart that I'm not going to go through in detail, but it just gives you an idea of the different possibilities. What we are going to be focusing on today is the sampling. Okay, very, very rapid sampling, very systematic sampling is key. And then for us, what we did is we looked at the lepili and the ash samples, so the explosively erupted samples that are rapidly quenched in contact with air. And then we did simple electron microprobe analysis targeting the glass fraction of the sample, so the quenched liquid representing that erupting magma. Okay. So the main questions that we're trying to target by doing this is we want to see if there is some sort of relationship between magma composition and what we see in the geophysical monitoring data. Okay, so that's the first research question. Another thing that we're interested in, is there a link between the magma composition that's erupting and the style of the eruption? Okay, and the La Palma 2021 eruption is an ideal testing ground for addressing these questions because the site was very accessible. Okay, it was easy to go there, and there was a lot of people available to sample the products. And also, the style of the activity was such that it was producing these near continuous strombolian to violent strombolian eruption plumes that produced a lot of tephra, and so we were able to sample it at a very high temporal resolution. Okay, so before we go further, I just want to introduce you to the case study a little bit, a background on the Canary Islands and La Palma. So these are the Canary Islands. They're located in the eastern Atlantic Ocean. They're intraplate volcanic edifices. The onset of magmatism is thought to have started about 60 million years ago on the seafloor, but the subaerial rocks are as old as 20 million years in the eastern part of the archipelago, and there's this progressive younging trend up to 1 million year old. These are the oldest subaerial rocks in the west. So there's this progressive younging trend, but it's discontinuous and definitely not as textbook as in the Canary Islands. The origin of these volcanoes is thought to be as textbook as in the Hawaii, I mean. So the origin is thought to be related to a mantle plume, some kind of mantle plume. And in the bottom figure here, we see this low shear wave velocity anomalies that seems to propagate, okay, all the way to the core mantle boundary underneath the Canary Islands. And this supports the plume hypothesis there. Okay. There have been 14 historical eruptions in the Canary Islands since the 16th century, and they've happened on 4 different islands, 2 on Lanzarote over here, 4 on Tenerife, most of them on La Palma, 7 of them here, and 1 on the submarine flanks of El Hierro. They've all been quite similar, involving this really alkaline mafic magma, and they've been quite small, except for one eruption. Okay, we can see it. This is the one we can see here on this map. The yellow lava flow field on Lanzarote is an order of magnitude bigger than the other ones, producing 3 to 5 cubic kilometer of lava. So focusing on La Palma now, La Palma is one of the youngest islands, and it's basically constructed by 2 main volcanic edifices. In the north, there's a basal complex made of, you can see the submarine stage of volcanism there, and it's overlain by an extinct shield volcano called Taburiente volcano over here. The southernmost tip of the island is what we call the Cumbre Vieja volcano. That's a ridge-shaped shield volcano featuring a single rift zone that is defined by the alignment of these cinder cones here. And that part of the island was constructed in the last 125,000 years. There have been 7 eruptions historically on this rift zone, most recently in 2021. And this is the 2021 lava flow field. It's a little bit bigger than the other historical eruptions there. Okay, the repose period has varied between 22 and over 2 centuries between eruptions. Okay. So the 2021 eruption occurred after 50 years of quiescence. Okay, the previous eruption was in 1971. The precursory activity lasted 4 years. Okay, and but at the time we didn't really know that anything was going to happen. There had been some small volcanotectonic earthquakes, swarms that have happened starting in October 2017, and they reoccurred in 2018 and in 2020, and then but the seismic activity really picked up only 8 days before magma breached the surface. Okay, so this is shown in this much accelerated unrest here, only 8 days. Okay, and this is blown up in this graph here. You can see the number of earthquakes picking up very, very rapidly. So that meant that there was very little warning that an impending eruption was going to happen, but enough for the authorities to take proper measures and evacuate the people. The tricky part was that we did not really know where the vent was going to breach. Okay, so this can be anywhere along this rift zone, but the earthquakes did provide some clues. During the eruption, before the eruption, you see this is the 8 days of pre-eruptive seismicity that essentially record the propagation of a shallow dike. Okay? But once the eruption had started, it was very interesting to see that the earthquakes accompanying the activity clustered at two distinct levels beneath the volcano. One in the mid to lower crust here, and one at mantle depth located over here. Okay? So I'll refer to these clusters as the shallow and deep clusters throughout the presentation. The eruption lasted 85 days, from 19 September to 13 of December of 2021. Amazingly, there was no casualties, okay, but a lot of destruction, up to about $1 billion US in infrastructure damage. 7,000 people had to be evacuated. Entire towns were destroyed by the lava flow, which covered 12 square kilometers with a 0.2 cubic kilometers of lava. And the tephra deposit was also substantial, 45 million cubic meters. And this is a house, okay, that was entirely buried by tephra. This is the cone that grew in this eruption. The house was about 800 meters away, and 4 meters of ash and lapilli accumulated, burying this house. So our work relies on this high resolution, high temporal resolution sampling. And how was this done in the field? So there were teams that placed these plastic containers at specific locations around the volcano, and also different distances based on the wind patterns. Okay, so if the wind was blowing a certain direction, we would collect samples, and then if the wind changed, we would always collect samples with this network of bins, essentially. And they were collected daily, and they were emptied daily, so we knew exactly when that ash was erupted. Okay. So we selected 85 of these tephra samples that are precisely dated, and we also used 4 duplicates. We have a daily resolution of this ash sample throughout the entire eruption. Okay, our samples cover 94% of the eruption time. Okay, so there's basically no sampling gap, which is quite incredible. From these samples, we selected 10 ash particles under the binocular microscope, which were representative. We mounted them in epoxy, we polished them, and then Samantha went to the American Museum of Natural History using the electron microprobe there, where she analyzed the glass phase. Okay, so these ash particles are made of glass and minerals. And so she collected points on the glass for major element composition, as well as sulfur and chlorine concentrations. We also did some textural analysis of the samples using image analysis of backscatter electron images. Okay, so what do the samples look like? Something like this. Okay, so we found 2 types of ash in these samples. The first type, which we call type A, okay, is characterized by this glassy luster, and it's dominated by glass. Okay, so in this backscatter electron image, the glass is the ground mass here, the gray phase. But there's also microlights of plagioclase over here, some olivine, quite a lot of clinopyroxene, and some iron titanium oxides. Okay, rare amphibole, rare apatite, and rare sulfides. The second type of ash had the same mineralogy, but the difference was that there was almost no glass. Okay, it's a microcrystalline ground mass, and in the hen specimen, this type of ash was not glassy, and it did not have a vitreous luster. It had like a dull luster. So our interpretation of these 2 types of ash is that type A ash represents the fragmenting magma. Okay, so it's a juvenile component that was directly ejected during the eruption. The type B ash is interpreted to have been modified through high temperature exposure after initial fragmentation. Basically, these are juvenile fragments of magma that have been recycled into the vent and then erupted later on. Okay, so they were fragmented, they went back into the crater, heated up again, and so that leads to this texture that we see. We can see the ash falling back into the crater, so that's a piece of evidence. And there's also been evidence at other volcanoes such as Etna. So that this is a juvenile recycled ash. Okay? So because this type B does not have any glass, we really focused on our analysis on the type A particles in which we can easily analyze the glass phase. Okay, so now we have this time series of glass analyses that I'm going to show you now. This is a total silica versus total alkali versus silica diagram, and our data is the circles. Okay, so this is all the glass data, and I'm also showing the squares here that are bulk lava compositions that were published by Day et al. In 2022. The color scale that I'm going to be using throughout these plots is related to the time of eruption. Okay, so the light yellow is early on in the eruption, and the dark red is late in the eruption. So what we see is that the glasses are tephritic in composition, and they have a slightly higher silica, higher alkaline than the bulk rocks, and they are much less rich in magnesium. So this is the magnesium over here. You see the bulk rocks are way up here, and the glasses are down here. It's expected because the glasses don't contain the ferromagnesium minerals that are present in the lavas. Okay. An interesting observation that we see from the bulk rocks is that there seems to be two groups. Okay, the early lava flows form a trend, and then the late lava flows form a different group. And the early lavas contain a lot of amphibole crystals, and were quite different petrographically. So there's evidence that there was at least two magmas involved in this eruption, where the first erupted stuff seems to have been a remobilized crystal mush that was forced to erupt by the invading basanite magma. So now we show the same data, but now as a function of time. Okay, so the color scale is kind of redundant with the x-axis here, but still I'm keeping it because it's pretty. Okay. So what we see is that generally the silica content, as well as the aluminum, sodium, and potassium, as well as sulfur and chlorine content, generally decreases, okay, up until the 10th week of activity. And in the last 2 weeks of activity, then these elements start to increase again. Okay, we can see this inflection point here. The compatible elements that go into the mineral assemblage, titanium, iron, magnesium, and calcium, show this opposite behavior. So you see increasing calcium and then decreasing calcium in the last 2 weeks of the eruption. So if we add the bulk lava composition on here from the published data set, we can see that the glass data shows much finer scale variations than the bulk rock. Overall, the bulk rock is almost flat, but we see a lot of variations in the glass. Another thing that we can see is that for some elements like iron, for example, okay, the trends in the glass and the trends in the bulk rock are completely decoupled from each other. Okay, for example, the inflection points that we see in silica content in the glass in the last 2 weeks is really absent from the bulk lava. Okay, so we think that this is probably a consequence of the bulk lava also being in training a huge crystal cargo that might be buffering the bulk lava composition. So we see more in the glass, and so this highlights that it's important to analyze glass if you want to see subtle changes in melt composition over time. So one thing that we have to worry about when we look at glass composition is that there's the possibility that late-stage formation of small crystals, okay, microlites, might have changed the melt composition. So what does the melt composition represent? Is it really from deep, or is it a shallow signature caused by small crystal forming, okay, at the late stage? So what we did here is we, for a subset of our samples, we collected high-resolution images and we traced out all of the crystals that are in the samples, and we measured the crystallinity. We found between 18 and 32 volume percent microlites, and they are dominated by plagioclase and clinopyroxene. And so we can take these glass compositions and use the crystallization vectors. Okay, so if we start from the more mafic glass and we assume 10% crystallization of each of the observed mineral phases, we can see if we can reproduce the data from crystallization. The main minerals that are forming are plagioclase and CPX, and they would take our composition in the opposite direction, okay, as the observed trend. So therefore, late-stage crystallization cannot explain the range of melt composition that we see. Okay, they must be representing distinct melt batches that are supplied from depth. How is the range of composition produced? Well, we have magmatic processes at depth, such as fractional crystallization and magma mixing, that can produce these ranges. Okay, so now we have these distinct melt supplied from depth, and we have this great time series of them. We wanted to compare these data with other monitoring data, and we're going to focus on 3 different data sets. The first one is the occurrence of discrete earthquakes beneath the volcano. This is a volcano-tectonic seismicity, shown in blue. The second data set is volcanic tremor. Volcanic tremor is this continuous seismic signal that accompanies the eruption, shown in green. This is a 6-hour average of the volcanic tremor amplitude. And then the third data set is the height of the eruption column as measured from satellites, and it's plotted in red here. So the eruption column height was on average around 3 kilometers height, but it reached up to 8 kilometers above the vent in the last powerful eruption pulse. Another thing I want to mention is that these discrete earthquakes, I've split them into 2 series because the depths were bimodal. I showed you this plot earlier. So the light blue is the shallow seismicity, and the dark blue is the deep seismicity. Okay, so if we take a closer look at the discrete earthquakes first, in comparison with our data shown in gray. So we first observed that there seems to be a relationship between the deep earthquake cluster and the shallow earthquake cluster. They show this similar sequence of peaks, okay, but the sequence is offset. These peaks have similar amplitude ratios and spacing. So like this peak might be this peak, this one, 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 this one. Okay? So if that's right, okay, it seems like this is tracking the supply of magma from depth to shallow levels. And another thing that we observe is that in the shallow earthquake swarms, we have a high frequency of earthquakes that correspond to break in slopes in the silica content of the glass. Okay, so we see it more clearly here but there's also a break in slope right here and here as well here. So what we interpret this to represent is that our data shows that the magma is changing composition, and the earthquakes are recording the injection of new melt batches that show up as distinct composition at the surface. Another thing we can do with this observation is that we can estimate the magma ascent rate from the mantle to the crust. Okay, so the time lag between these earthquake swarms is not the same throughout the eruption. In October, it's about 15 days, 13 to 15 days, and in November and December, it's between 6 and 8 days. Okay, the lag between the deep and shallow earthquake swarms. If we assume that this tracks the ascent of magma over a vertical distance relating to the difference between the depth of the deep and shallow swarms, we can estimate magma ascent rate. Okay, and this leads a 1 centimeter per second, okay, in October, and about twice as fast, or to 3 times as fast, in December and November. So that's pretty neat. It's relatively slow, okay, but this is at depth. This is from the mantle to the crust. Magma ascent obviously accelerates dramatically at shallow levels, reaching tens of meters per second, maybe hundreds of meters per second, as the magma is being ejected at the vent. Okay. Next thing is we want to look at the relationship with the tremor. So the tremor is this continuous seismic signal accompanying the eruption. And what we see is that there seems to be a broad correspondence between the silica content of the glass and the tremor. Over short time scales, okay, there's definitely some mismatches. So if, for example, over here, the tremor is much higher, okay, and it's not corresponding to an increase in silica content. So these mismatches between the tremor and the glass composition often corresponds to when there is in shallow earthquake swarms. So it seems like the influx of magma creating the earthquake swarm also is causing an increase in tremor. So when we look at our data against the eruption plume height, we see very little relationship there. Another approach to do the same is we can average, okay, the monitoring data for the exact time span that correspond to our samples. Okay, so when we do this, we can plot the variables against each other into these bivariate plots. And what we find, we find this weak but statistically significant correlation between the tremor amplitude and the glass silica content, but no correlation with the other parameters we looked at. Okay, so this correlation suggests that there is some control of melt composition on the amplitude of volcanic tremor. This has not been observed elsewhere before, and there's no straightforward mechanism to explain this at first. So we see when the melt composition is high in silica, we have high tremor, and when the silica content is low, we have low tremor. But why? Okay, so what is the mechanism? So we'll have to take a few detours here to try to explain this relationship. Okay, so the first thing we got to ask is, what really is the tremor? What does it record? What is the source of the tremor? Okay, so one key clue there is that the tremor is only present when the volcano is actively erupting. Okay? When the eruption stops, the tremor stops. And at Piton de la Fournaise volcanoes, a similar volcano in the Réunion Island, the tremor signal there has been studied in a lot of detail. And what they found is that the source of the tremor is coincident with the site of the eruption. Okay, so the source is at the same location as the eruption site, It's also very, very shallow. In the upper few hundred meters, or maybe even possibly at the surface. Okay. So this is the histogram of the estimates of depth sources of the tremor, and most of them seem to be shallow, and this corresponds to where we'd expect the water to exsolve from the magma, and so where the gas content of the magma becomes quite important, and the gas volume fraction increases dramatically. So this suggests that what is the source of the tremor is degassing, shallow degassing, outgassing of the magma right beneath the vent. Okay, so if we accept that, we also should think about how magma degassing is occurring beneath basaltic volcanoes. Okay, so there's three main regimes of outgassing beneath basaltic volcanoes that depend on gas flow rate and produce different eruption styles. At low gas flow rates, we have what we call the bubbly regime. Okay, so we have a lot of melt and only a little bit of gas, and this produces effusive eruption style. At slightly higher gas flow rate, bubbles start to coalesce together, forming these big gas slugs. Okay, so the blue in this cartoon, the blue is the gas phase and the red is the melt phase. And so you can see these big gas slugs here rising in the conduit, and when they breach the surface, this creates a strombolian explosion. Okay. At even a higher gas flow rate, the gas phase is dominating in the conduit and basically is propelling the melt phase with it in what we call the annular regime. And this causes lava fontaining, vigorous lava fontaining at the surface. Okay, so now to get back at this seismic signal, okay, we can look at some analog experiments as well as numerical experiments that have looked at this. And so these experiments are particularly interesting and novel. They set up these cylindrical conduits of different shapes, okay, and they use different gas fluxes injected at the bottom of the cylinders, and they use different liquid viscosities. Okay, so to look at the effect of liquid viscosity on the gas flow, and also they measured the seismic signals and the acoustic signals caused by the ascent of gas bubbles and the bursting of gas bubbles at the surface. So that's pretty neat experiments. I've compiled these data and I've replotted them to look at some interesting parameters. On the left plot here, I'm plotting the gas flux in the experiments versus the observed degassing regime, so bubbly, slug, and annular regimes. The color scale here is the seismic amplitude, so the green is low seismic amplitude, dark blue is high seismic amplitude, and the symbols are different liquid viscosities. Okay. So the experiments could test the influence of gas flux, melt viscosity, and the conduit geometry. What we're seeing is that the gas flux has a strong effect. Okay, so with increasing gas flux, we have transition in the degassing styles, and also there's strong increase in the seismic amplitude. So if we take, for example, the high viscosity experiments, okay, at low gas flux, the seismic amplitudes are low, and at high gas flux, they are high. Okay. Also seen on this other plot where I'm showing seismic amplitudes versus gas flux, we can see a correlation. But there's also a cool effect of melt viscosity in these experiments. Okay, so the at higher melt viscosities, there's a transition in the degassing styles that happen at lower gas flux. So for example, in the slug regime, when we have these big gas bubbles, okay, in the low viscosity experiments, it's able to sustain this slug regime up until a higher gas flux. But in the higher viscosity experiments, it takes only a small gas flux to transition to the more explosive degassing regime, which is the annular regime. Okay? And for the very high viscosity experiments, any gas flux lead to the annular flow regime. So I think there's interesting clues there that melt viscosity does play a role. And another interesting observation is that if we keep gas flux constant and look at a single flow regime, so for example in the annular flow, an increase in viscosity tends to yield higher seismic amplitudes. Okay, so this is maybe best seen in this diagram all over this gas flux. If you look at a constant gas flux, the higher viscosity yields higher seismic amplitudes. Okay, so another set of experiments were done to look at overpressure inside the gas bubbles and the gas slugs that form beneath basaltic volcanoes, and they found that increasing melt viscosity should yield to higher pressure inside these bubbles as they ascend, and when they burst at the surface, this triggers a seismic signal of greater amplitudes. Okay, so viscosity could be related to the seismic signal. And this is a numerical models that show that the burst overpressure of these bubbles is greater when the viscosity is higher than when it is a bit lower. This is a small difference in melt viscosity only. Okay. So now, gas flux and viscosity controls are potential lines of in investigation. So if we go back to La Palma, can we test whether gas flux or melt viscosity might be at might be related to the tremor amplitude? The best thing we can do for a gas flux is to look at sulfur dioxide emissions that have been monitored by satellite data. Okay, so this is the Tropomi satellite, okay, showing a concentration of sulfur dioxide in the atmosphere above the Canary Islands during the eruption. And if we convert that to a SO2 mass per day, we can plot it as a time series, and this is the black line here. Okay, it goes up and down, but overall, the SO2 emissions was high at the beginning of the eruption and declined over the course of the eruption. Tremor was also high at the beginning of the eruption, but then it doesn't really decline that much over the course of the eruption. So if we can also do a bivariate plot, tremor amplitude versus SO2 mass on a daily basis, and we don't find a very strong correlation there. So there's not a good suggestion that gas flux is the control. Okay, we can take a look at melt viscosity. Okay, we can calculate melt viscosity from our data. Okay, so we have the melt composition from our glass measurements, and there are good models to calculate melt viscosity. It's strongly controlled by the SiO2 content of the magma as well as the dissolved water content. Okay, the dissolved water content in turn is controlled by the depth, the pressure. Okay, because that controls water solubility. At the shallow depths where the tremor is generated, the water has mostly exsolved from the magma, so the more appropriate viscosity is the anhydrous viscosity, where the water has been completely exsolved. So we can calculate melt viscosity here as a function of water content and SiO2 content. This is a low SiO2 content melt viscosity and high SiO2 content melt viscosity. And we can see that at low water, corresponding to shallow depths, we have about a 1 order of magnitude change in melt viscosity. Okay? So if we plot, instead of plotting SiO2 content, we can plot melt viscosity, and we do find the same correlation between tremor amplitude and melt viscosity. Okay? So our idea is that this is what's happening. Okay? So melt viscosity, controlled by silica content, is changing the pressure regime of degassing beneath the volcano, and that creates a higher tremor amplitude for high silica scenario versus the low silica scenario. So we have slower bubble ascent when the viscosity of the melt is high, and greater bubble overpressure as the bubble bursts at the surface. In the low silica content scenario, the bubble ascent is faster and the bubble overpressure is smaller. That yields to a smaller amplitude of the seismic signal. Okay? So, to summarize, we've performed this petrological monitoring, and the key there was to have a very high temporal resolution sampling campaign, about a sample per day, sometimes more, during the La Palma eruption. We analyzed the glass composition to get a record of shifting melt composition over time, and that was a high enough resolution that we could compare it with other traditional monitoring data sets. We found this broad correlation between the silica content of the glass and the amplitude of the volcanic tremor, which is intriguing, and that translates also to a correlation between melt viscosity and tremor. And so from digging into numerical models and as well as analog models, we are getting a hint that this relationship is due to the effect of viscosity on the degassing regime and the pressure of bubble burst that caused the tremor beneath the vent. Okay, so this is interesting because it can provide new insights to interpret volcanic tremor during basaltic eruptions. Okay? Sometimes we don't really understand why the tremor amplitude is changing, and that might be one of the reasons. So if we return to our research questions, so is magma composition linked to geophysical monitoring data? Yes. Okay, so we see changes in SiO2 content that are related to the occurrence of shallow seismic swarms that we think are recording influx of new melt at shallow depth that come from the mantle. There's also this relationship between SiO2 content and tremor, and we suggest that this is due to a viscosity effect controlling the tremor amplitude. And then the second question was, is there a relationship between magma composition and eruption style? And there we did not find anything particularly interesting, at least with eruption style quantified by these satellite derived plume heights. Okay, so but one other important conclusion here is that this approach demonstrates that high temporal resolution sampling of volcanic ash is a really useful tool for monitoring of volcanoes. The tricky thing is to get the data fast enough, okay, to inform the authorities in real time. So thank you so much for listening, and I'll be happy to take any questions. Thank you.
Thanks. Yeah, questions for Marc-Antoine? Maybe we could start with
I know there's a lot there. Yeah, thank you.
Yeah, so you were measuring the chemical composition of Teflon, or the glass part of Teflon, in the probe.
Yeah.
And how far away was the probe in this case? Was it like?
Well, so in that case, it's in New York City, so very far.
Oh, very far. So you're not even close yet to getting real time.
So to get real time, there either has to be a very efficient shipping of samples, but preferably we would need an SEM, okay, an SEM on site. We were able to get data during the eruption. So we were able to get the first batch of data a few weeks after they were collected. So in our case, it's a hindsight, so we can demonstrate that it could be useful to do this in real time. But yeah, there were limitations in getting the samples out of the island. That was the main thing, because we were ready to analyze them as soon as they were getting to us, but getting the samples, besides the one you go to collect yourself, right? We did that. The first 3 weeks of the eruption, we have our own samples, but after that, yeah. So it's a challenge. Yes.
So you didn't find any correlation between composition and plume height. So what do you think is controlling the plume height?
Well, it's a good question. So these plume height measurements from, it's unclear what they, like if they really record the explosivity of the eruption pulses. So I think in some cases, yes, but they were almost always the same. So there was like a wind effect as well that people have come up with, but I don't know. I wish that there would be another measure of the eruption style than the top of the ash plume height. There hasn't been in this case. What would be interesting to measure is also like the height of the lava fountain. That would be good, but we don't have data for that. Yeah.
Yeah, I was going to ask if you had video data like this that you could get lava fountain height or the velocity of that initial.
Yeah.
So they were doing in Hawaii and
Yeah. Well, I mean, this type of data exists, but in a very short time span, usually. So people they measure it for a few days, but over the entire course of the eruption, it doesn't exist for this eruption. Yeah. Yes.
On the first plot that you showed that suggested that relationship between the silica content and CCC, can you go back to it? There are some peaks that you can match, but there are some compositional mismatches.
Yeah.
Even earlier.
This one?
Yeah, there, yeah, let's try that one. Like, you can see that there is some matchability. You go to the next slide, you can see again. How do you explain the discrepancies?
So the volcanic tremor is a very complex signal. People wonder a lot about what is actually causing it. So I think the viscosity seems to be one factor, but it's not the only factor. There's a lot of other things that are causing tremor amplitude to change. For example, the mass flux, so if there is a change in supply rate of the magma, that could be increasing the tremor amplitude. So I think that might be what we're seeing with when there is like a swarm of shallow earthquakes, suggests there's a new batch, maybe a more voluminous batch of magma coming in, and that the blue line, the blue peaks precede the green peaks by just a little bit. Okay. So that so I think that there's a big mismatch between the viscosity or SiO2 and viscosity here and the tremor, and this is when we have these shallow earthquake swarms as well. So that could be where the mismatch comes from there.
Do they have anything to do with the rate of cooling or the chemical change in the crystals that are basically that's forming around as so you've got the fluid coming up, the material coming up, you've got this shell around it that is probably through. Does it have anything to do with that? Composition of the
I'm not sure. Like, so the cool. You're picturing like cooling in the conduit?
Yeah, and that will change as you've got material coming up in different pulses. Does that happen?
I don't know. So volcanic conduits are tricky. So we don't know exactly what they look like. When the eruption first starts, we know it's a dike. Then it focuses at one eruption site. We don't really know what's the geometry down there, but I'm assuming it's a dike, okay, about a meter wide at depth, something like this, because this is what we see in the rocks. Well, yeah, I don't know how to answer your question really, because we don't know what's with the geometry down there. Yeah.
Did you find any other products other than ash coming from the volcano?
Yeah, so there was like a lot of lava produced by this eruption. Most of the volume is lava, but the lava cools relatively slowly, so we can't use it to analyze the glass. That's why we focus on the ash. But there's also like coarser particles closer to the vent. You'd have like lapilli and big bombs as well. So there are a lot of different products from this eruption. Yeah.
Are there any mantle xenoliths that?
I think there are some very small mantle xenoliths in this, and there's also some crustal xenoliths.
Are those small xenoliths, are the timescales consistent with sort of the lag that you're seeing from deep to shallow, if those peaks are really matching up like you think?
What do you mean the time scales?
Like if you did the xenolith settling rate
Oh.
calculation.
These lavas are really poor in xenoliths, so nobody has really looked at that yet. And in the field, we kind of looked for them. And there's a few, but they're like this big. Yeah, there might be some bigger ones, but we haven't found them. Like I haven't done that math.
I guess that on some level is reassuring. Like if there is a really slow transit from deep to shallow, if you want to interpret the xenoliths as recording that transit,
Yeah.
you would hope there are not many. How about diffusion modeling? Is that consistent with the
it's not. We don't. Well, the diffusion modeling has not been published, but we have some data that suggests days to weeks of between mixing at depth and eruption. So yeah, it's consistent with that ascent rate within the bounds of big uncertainties. Yeah.
Thank you again, Marc.
Thank you.